Welcome to this explainer. Today we are cracking open an everyday treat to reveal the highly engineered molecular science hiding right inside your favorite candy bar. Yep, we're talking about chocolate. And we aren't just talking about taste today, we're actually decoding the exact chemical structures that make it so incredible. I promise you, by the time we finish this, you will never look at a piece of chocolate the same way again. Okay, let's dive right into this. It's a sensory mystery that pretty much everyone has experienced, but, very few of us actually stop to question it. Think about that snap. That exact, clean snap when you break a really good bar of chocolate in half, followed by how perfectly it melts the second it hits your tongue. None of that is an accident. It's certainly not just good marketing. That famous snap and melt are literally engineered down to the molecule. If the chemistry is even slightly off, your chocolate turns into a gray, chalky mess. So why exactly does it melt in your mouth, but stay completely solid when you're just holding it? Well, the answer comes down to this very specific number, 93. That's 93 degrees Fahrenheit, or roughly 34 degrees Celsius, which happens to be just shy of our natural human body temperature. Chocolate stays completely solid sitting on the kitchen counter, but melts instantly on your tongue because of a remarkably strange ingredient called cocoa butter. Now, cocoa butter is a triglyceride. That basically just means it has 3 fatty acid chains hanging off a central glycerol backbone. But cocoa butter is arguably one of the weirdest fats found in nature, and it is entirely responsible for this exact 93-degree melting point. Moving into Section 1, the perfect snap, deconstructing the melt. To really understand how cocoa butter behaves, we have to look at how it freezes, or more accurately, how it crystallizes. Unlike most of the fats you might cook with, cocoa butter doesn't just have one simple solid state. It can actually form into 6 completely different structures. Scientists call these forms I through V. But here's the crazy part. Out of all 6 potential crystal structures, only one actually tastes good, and that's form V. It's the specific crystal lattice that delivers that glossy shine, that clean snap, and that perfect melt-in-your-mouth experience. If the cocoa butter crystallizes into forms I through IV or form V, you are left with chocolate that is dull, soft, crumbly, or melts at completely the wrong temperature. Form V is the absolute holy grail. It's where all the magic and honestly, the whole yum factor lives. Section 2. Crystallography with dessert, exploring the chemistry of tempering. Now, getting that perfect Form V crystal isn't something that just magically happens by tossing chocolate in the fridge. To get the right texture, the manufacturing process has to be incredibly precise. When you watch a master chocolatier working melted chocolate on a marble slab, you shouldn't just see a chef following a recipe. You should actually see a scientist manipulating crystal structures. It requires a precise scientific process called tempering. First, you melt the chocolate, and if you melt it too hot, every single crystal form dissolves completely and you're essentially starting from scratch. Step 2 is to cool it down. But if you cool it slowly, those unstable, ugly crystal forms start showing up first. So step 3 is the absolutely crucial one. You have to gently reheat the chocolate to a very specific narrow band of temperature. For dark chocolate, that's exactly 88 to 90 degrees Fahrenheit. Hitting that specific temperature window is exactly what coaxes the cocoa butter into locking into that perfect Form V lattice. But what happens if you skip that exact science? Well, you get something called chocolate bloom. You've almost certainly seen this before. It's that white, gray, kind of chalky film that sometimes appears on older chocolate, or maybe a chocolate bar that's been left out in a warm car. Let me assure you right now, it is not mold. Your chocolate hasn't gone bad. It is simply fat chemistry gone rogue. What's happened is that the fat crystals have actually migrated and reformed into one of those less stable, ugly structures we talked about just a minute ago. It's the exact same chocolate holding the exact same ingredients, but because the chemistry shifted, it has a totally different look and a pretty terrible texture. Up next is Section 3, building complex flavors, from bitter to bliss. So we've nailed down the texture, but let's pivot over to flavor. Here's a pretty wild fact. Raw cacao beans are actually highly bitter and astringent. Honestly, if you were to crack open a cacao pod and eat a raw bean right there, you'd find it pretty unpleasant. To build that distinct chocolate flavor you know and love, the beans have to go through a fascinating chemical journey. Step 1 is fermentation. The beans are piled up, often covered in banana leaves, and just left for several days. During this time, yeast and bacteria break down the sugary pulp surrounding the beans. This process generates acids and alcohols that literally seep into the bean itself, creating hundreds of flavor precursors. But wait, they still don't taste like chocolate, not until step 2, roasting. Roasting triggers the exact same heat-driven chemistry that browns a steak or toasts a piece of bread, the Maillard reaction. Under that heat, the amino acids and sugars inside the bean literally collide and rearrange themselves into hundreds of brand new, beautifully aromatic compounds.
And comparing the raw numbers brilliantly illustrates just how effective that roasting process really is. Think about a typical strawberry. It contains about 30 distinct flavor and aroma compounds. Roasted cacao? Scientists have identified over 600 distinct flavor compounds in a single roasted bean. That's insane. The sheer staggering complexity of chocolate's flavor honestly rivals fine wine and specialty coffee. And remember, that is almost entirely a product of that heat-driven Maillard chemistry we just discussed.
Section 4, the chemistry of bliss, the feel-good molecules. Okay, so we know why it snaps and we know why it tastes so ridiculously complex, but why does eating chocolate actually feel so good? It turns out it's not just a lack of self-control on our part. There is a real, hard chemistry behind the chocolate high. It actually comes down to 3 trace molecules. First up, we have theobromine. This is a mild stimulant that's closely related to caffeine. Next is phenylethylamine, which scientists sometimes nickname the love molecule, because your brain naturally releases it when you feel excited or attracted to someone. Finally, there's anandamide. The name actually comes from the Sanskrit word for bliss, and it's a compound that binds to the exact same receptors in your brain as cannabis. Now, to be clear, these are trace molecules. You're not going to get high off a candy bar. But when you combine these 3 specific molecules with a satisfying hit of fat and sugar, it lights up your brain's reward pathways in a way that very few other foods on the planet can match. Which brings us to our final section, hiding in plain sight, the structural secret. There's one final hidden ingredient we absolutely need to talk about to truly understand chocolate chemistry. See, we have a fundamental problem in our mixture. Cocoa solids are hydrophilic, meaning they love water. But cocoa butter is hydrophobic, meaning it actively repels water. If you just left them alone, they would separate out exactly like oil and vinegar in a salad dressing. To keep them together, manufacturers use lecithin. It's an emulsifier. Structurally, it's this tiny molecule with one water-loving end and one fat-loving end. One side grabs onto those hydrophilic cocoa solids, and the other side grabs onto the hydrophobic cocoa butter. It acts like a bridge, holding the entire mixture together in one perfectly smooth, stable blend. Without this tiny structural secret doing some very heavy lifting behind the scenes, your chocolate would just be a grainy, split mess. Ultimately, chocolate is, without a doubt, the ultimate engineered food. Every single sensation you experience when you eat it is chemical perfection. That sharp crack, that's the highly unstable Form V crystal lattice. That rich smell, that is the Maillard reaction, a piece of culinary chemistry hundreds of years in the making. That rush of happiness you feel, that is a literal cocktail of stimulants hitting your reward pathways that your brain evolved to love. It isn't just a sweet treat. It is molecular science that somehow tastes like pure magic. Which leaves me with this thought for you to ponder. We just deconstructed a candy bar down to its very atoms, but our kitchens are absolutely full of mysteries just like this. What other everyday foods are hiding incredibly complex chemistry just waiting to be cracked open? Could it be the compounds in your morning coffee? Or maybe the fermentation science inside your favorite cheese? Let this explainer be a reminder that there is fascinating science hiding in plain sight all around us, especially in the things we eat every single day. Keep learning, keep questioning, and I will see you in the next explainer.